Hello, everyone. Around the end of the 19th century, the scientific community was deeply interested in phenomena related to the electron, especially experiments with cathode ray vacuum tubes. At that time, the electron had only just been discovered. Most physicists across the world were quietly racing to be the first to uncover new and exciting phenomena connected to this particle. Among them was Wilhelm Röntgen, a German physicist and professor at the University of Würzburg. In 1895, he designed an experiment with a cathode ray tube to determine whether the rays could pass through certain materials, such as glass. At first, Röntgen used a vacuum tube wrapped in black paper, hoping to better observe any rays emitted during the experiment. About 1 meter away from the tube, he placed a fluorescent screen made from barium platinocyanide, a compound known to glow when exposed to energy. When a high voltage was applied, the cathode tube began to discharge. Röntgen expected to see a beam of cathode electrons pass through the black wrapping, or at least cause the fluorescent screen to glow. However, reality did not match his expectations. He saw no visible cathode rays, yet faint, scattered glimmers appeared on the screen. The closer he brought the screen, the brighter and clearer the glow became. He wondered if these could be scattered, discrete cathode rays too faint to see. But when he placed a magnet in their path, the rays did not bend. The screen continued to glow. This proved the rays were not cathode rays, since they were unaffected by magnetic fields. After repeated tests with different shielding materials, books, wooden boards, thin sheets of metal, even his own hand, he discovered that these mysterious rays could penetrate matter, blocked only by dense substances like lead or bone. Röntgen called them X-rays, X for the unknown, because no one had ever encountered them before. He deduced that they were a secondary product created when cathode electrons struck the glass walls of the tube or its metal electrodes, producing high-energy emissions. In terms of their nature, X-rays were unlike cathode rays or ordinary light. They could penetrate matter, strongly ionize, and were immune to magnetic influence. Their discovery was a historic milestone, helping scientists understand atoms and high-energy electromagnetic phenomena. Above all, X-rays would soon become indispensable in modern medicine. After Röntgen announced his findings, the scientific world was stunned. His discovery sparked new lines of research everywhere. Henri Becquerel, a French physicist, grew curious about Röntgen's results. He wondered if high-energy cathode rays could generate X-rays that made fluorescent materials glow. Could other phosphorescent materials, when exposed to sunlight, produce similar emissions? To test this, he chose uranium potassium sulfate, a salt known for strong fluorescence, with the formula K2UO2SO42. His experiment was simple. He wrapped a photographic plate in opaque black paper to block all light, placed a uranium salt crystal on top, and exposed it to sunlight. According to his reasoning, the salt would absorb ultraviolet radiation, rise to a higher energy state, and emit secondary radiation that might fog the plate if X-rays were produced. Indeed, after exposure, the plate showed a darkened spot where the crystal had been. To be sure, he repeated the experiment on cloudy days when there was no sun, and the result was the same. From this, Becquerel concluded that uranium salts emitted radiation spontaneously, without needing sunlight or external stimulation. This radiation could penetrate matter even more strongly than X-rays, ionizing the air and creating charged particles. Unlike X-rays, it was not triggered, but occurred continuously as a natural process. Becquerel called it uranium radiation. This spontaneous emission fascinated scientists, as it was unlike anything they had seen. No one knew its mechanism or why it occurred naturally. In 1897, Pierre Curie, a French physicist, and his wife, Maria Skłodowska, a Polish chemist, better known as Marie Curie, decided to study this phenomenon in depth. To measure such faint emissions, Pierre designed a highly sensitive device called an electrometer. According to physics, if uranium emitted radiation spontaneously, it would ionize nearby air, creating tiny changes in electrical charge. The electrometer could detect these minute variations, making it a powerful research tool. Marie Curie began measuring uranium samples and confirmed Becquerel's findings. She observed that uranium's radiation did not depend on its chemical form. It was the same in every compound. More uranium meant stronger radiation. This showed that the emission was an atomic property, not a chemical one. In 1898, analyzing uranium ore, the Curies noticed something remarkable. Even after removing all uranium, the residue was more radioactive than pure uranium itself. This suggested the presence of unknown elements. In July 1898, after painstaking chemical separation, Marie Curie identified a new element that emitted radiation 400 times stronger than uranium. She named it polonium, after her homeland, Poland. A few months later, they discovered another new element, one with 1,000,000 times more radiation than uranium. In darkness, it glowed green and continuously released heat. They named it radium, from the Latin radius, meaning ray of light. With these discoveries, Marie Curie coined the term radioactivity to describe spontaneous atomic emissions. From 1899 to 1902, she processed tons of ore to isolate radium. In 1902, she finally obtained 0.1 grams of pure radium chloride and determined its atomic weight to be 226. In 1903, Marie and Pierre Curie, along with Henri Becquerel, were awarded the Nobel Prize in Physics for their work on radioactivity. In 1911, Marie Curie won a second Nobel, this time in chemistry, for discovering polonium and radium and studying their properties. To this day, she remains the only woman to receive 2 Nobel Prizes in 2 different scientific fields, and the first woman Nobel laureate. In 1935, her daughter Irène Joliot-Curie also won the Nobel Prize in Chemistry, making the Curie family one of the most celebrated Nobel dynasties in history. At the dawn of the 20th century, radium caused a sensation. People marveled at its magical qualities, glowing in the dark, releasing heat endlessly like an eternal furnace. Its uniqueness sparked a craze. Radium was advertised as a health elixir, believed to rejuvenate the body and enhance vitality. It was added to cosmetics like creams, powders, and lipsticks, and even to drinking water marketed as radium water. In the 1920s, many workers, mostly women, were employed in factories painting luminous radium dials on watches and instruments. They were instructed to lick their brushes to a fine point, unknowingly ingesting the deadly substance. Tragic illnesses and deaths followed, remembered as the Radium Girls disaster. Marie Curie herself, after years of direct contact with radioactive substances, developed leukemia and died in 1934. Incredibly, it was not until 1938 that the U.S. Food and Drug Administration officially banned the use of radium in food and cosmetics. When accepting the Nobel Prize in 1903, Marie Curie once said, "Radium is for the service of humanity." she never imagined it would also bring disaster. The discovery of radioactivity had shifted from a thrilling breakthrough to a terrifying revelation. The effects of radium poisoning were catastrophic. Once inside the body, radium replaced calcium in bones, releasing alpha particles that destroyed surrounding tissue. In truth, Marie Curie was a chemist. She could not have foreseen that atomic phenomena could unleash such immense energy with such devastating consequences for human health. But why is radioactivity so dangerous? Why do atoms emit particles at all? What is the fundamental mechanism behind it? We will explore these questions in another video.